يلا سوا يا شباب. Okay, at the end of the session. Good morning, everyone.
Morning,
It's a pleasure to welcome you back to the LCWE Cross-Learning GIS School. I would like to begin by sincerely thanking all of you. Your commitment and active participation throughout this training journey are what truly drive the success of this advanced GIS school. Let us briefly return to the core goal we set in our very first session. Our purpose was never simply to learn new software tools. We aimed to equip you with the scientific methodology, the capacity to confront really environmental and water challenges by progressing from observation to analysis, prediction, and automation. In this school, we are building a solid bridge between silent data and informed decisions that support the LCWE Center's research and applied studies. So far, we have progressed through two major stages of our methodological journey. In session 1, we established the scientific foundation. We learned how to convert satellite imagery from visual pictures into quantitative scientific data, how pixels represent physical surfaces, and how enhancement techniques and spectral indices allow us to extract environmental information hidden with raw imagery. In session 2, we entered the decision-making stage. We moved from imagery to interpretation, learning how to transform billions of pixels into spatially meaningful information. We mastered advanced classification techniques from supervised classification, unsupervised classification, object-based image analysis, and deep learning, and then translated these results into suitability modeling and spatial decision support. Using the rainwater harvesting ponds case study as our real-world application. Today, we take the final scientific step. We move from image classification toward real-world environmental decision-making through hydrological modeling and automation. If session 2 answered the question, what is on the Earth's surface, then today's session answers a deeper and more dynamic question. How do natural processes move, and how can we predict, simulate, and automate their analysis? So until now, we have learned how to transform satellite imagery into accurate land cover maps. These allow us to extract reliable surface information. However, classification alone is not our final goal. The critical question is, how do we convert these maps into practical tools for water resources planning and land management? This is where hydrological modeling becomes essential. We will shift from static mapping to hydrological modeling, and we will explore how automation and deep learning transform GIS workflows from manual procedures into intelligent, automated system capable of handling complex environmental processes. Now that we have a solid conceptual foundation, let's outline our practical roadmap for today. This session is structured around four intelligent integrated scientific themes that reflect the full GIS environmental modeling workflow. The first theme for today will be about terrain-based hydrological modeling foundations. We want to understand and generate DEM, derived hydrological layers that define real water movement across the landscape. The second theme for today will be about deep learning driven land cover integration. We talked a little about the last session. Integrating advanced deep learning classification outputs as a dynamic model inputs, ensuring accurate representation for surface conditions that directly control the runoff or the infiltration and suitability outcomes. The third theme will be about workflow design and automation, Model Builder and ArcPy, designing scientifically correct hydrological workflows in Model Builder, converting them into executable ArcPy scripts, enabling batch processing, scenarios testing, large-scale model deployment, and automated updating of analysis as the new data becomes available. The final theme will be about multi-criteria decision modeling for water resources planning, applying weighted overlay analysis to combine hydrological variables, terrain factors, and classified land cover into decision support and suitability maps that guide evidence-based planning for rainwater harvesting, watershed management, soil conservation, and sustainable land use. This workflow guides us from accurate surface classification through physically based hydrological modeling into a scalable automation and finally toward a real-world spatial decision making. Each stage is scientifically linked to the next, ensuring that our GIS analysis move beyond visualization into operational environmental modeling. Before we start building models, let's clarify why hydrological modeling is critical. First, hydrological modeling allows us to understand how water moves across the landscape, how rainfall translates it into runoff, where water accumulates, and how watersheds interact, and which areas are most suitable for water harvesting. In this, it is the foundation for answering applied questions such as where will surface concentrate after rainfall, which areas contribute the highest water volume to a given outlet, where are the most suitable zones for building rainwater harvesting ponds or implementing soil conservation measures. This is critical and fundamental for sustainable irrigation planning, rainwater harvesting, for flood management, for soil erosion prevention, and ecosystem conservation. To perform hydrological modeling properly, we rely on several key inputs that drive water movement across the landscape, each of which plays a distinct and scientifically necessary role. digital elevation model أنا حطفي هيدا الميتنج حنين عشان الصوت بس ضلك أنت متابعة الشخص. First, a digital elevation model. Second, land cover maps. Third, rainfall and soil parameters. Fourth, hydrological layers. We will start with the digital elevation model, DEM. When the DEM provides the terrain structure of our study area, elevation data allows us to calculate first slope, how to control runoff velocity and erosion risk, aspects influencing solar exposure and soil moisture, flow direction, defining where each pixel drains, flow accumulation, identifying a natural water convergence zone. The DEM tells us how gravity guides water movement across the landscape. Without it, we can't determine realistic flow paths or watershed boundaries. Hydrological modeling simply becomes impossible. The second input is about the land cover maps. It's the second essential input, comes directly from our remote sensing workflow, which is the land cover map produced by classification. Land cover determines surface roughness, infiltration rates, and runoff potential. It determines how water behaves at the surface. Such as bare soil generates a higher runoff due to a limited infiltration. Dense vegetation increase infiltration and reduce flow velocity. Also, urban areas show the highest runoff due to the complex surface. Our progression from pixels, OBIA, deep learning exists precisely to improve the accuracy of these surface categories. Misclassified land cover layer leads to incorrect runoff estimates and flawed suitability map. Therefore, classification accuracy directly determines the reliability of the hydrological model. Now you may wonder, how does our work in image classification, the last session, connect to this? Remember our workflow from pixels, OBIA, deep learning. Classification is not making maps. It creates accurate land cover representations, which are essential inputs for hydrological modeling. For example, bare soil, vegetated area behave differently in runoff. OBIA and deep learning improve map precisions, ensuring reliable hydrological layers, flow accumulation and slope, runoff, etc. Without accurate classification, hydrological models would be weak. The better the classification, the more robust the analysis and actionable the decisions. Today, we connect image analysis directly to environmental decision making, enabling evidence-based interventions. So with the deep learning integration, we make enhancing land cover accuracy. Deep learning refines land cover maps beyond pixel or object level features. The traditional classification can misclassify mixed or heterogeneous areas, as we said and mentioned. CNNS and other deep models learn complex spatial and spectral patterns to improve accuracy. Example we can use in such cases, distinguishing dense shrubs from bare soil in hilly regions, differentiating built-up areas from shadows in urban zones, and enhancing hydrological modeling inputs for more accurate runoff predictions. The third input for this model is are rainfall and soil parameters. Because hydrology is incomplete without precipitation data, which represent the actual water input driving the system. Accurate rainfall records ensure that runoff and accumulation estimates reflect real meteorological conditions rather than theoretical assumptions. Additionally, soil infiltration parameters control how much rainfall turns into surface flow, how much infiltrates into the ground. For example, the sandy soil absorb water quickly, so there is generating lower runoff compared to compact clay soils. These inputs connect climate and soil science directly to GIS-based modeling. The fourth input is derived hydrological layers. Using the digital elevation model, DEM, inside ArcGIS Pro, we can generate first flow direction layers that describe drainage paths. Flow accumulations layers highlighting water convergence zones. Watershed boundaries produced by defining outlet points, which is the pure points, and delineating contributing areas upstream. These layers represent the dynamic behavior of water on the landscape. They allow us to quantify how much water reaches specific locations, which areas contribute most to runoff, where natural concentration points occur. So in general, each input is critical. DEM gives structure, land cover gives context, hydrological layers provide dynamics, and together they feed decision-making models. The sequence for hydrological modeling in ArcGIS Pro is very important. We must be confident that we are applying the hydrology tools in the correct scientific sequence. Hydrological modeling is not a random collection of tools. It follows a strict workflow defined by how water physically moves across terrain and how digital elevation models represent that movement. If even one step is missing or preformed out of order, the entire model becomes unreliable. Let us walk through this sequence step by step. Step 1, which is a fill tool, which means preparing the surface. The first and most fundamental step in hydrological modeling before running any hydrological tool. Why we use it? Because natural dams often contain artificial depressions known as sinks. Cells or groups of cells surrounded by higher elevations that trap water digitally, even when no such depressions exist in reality. These sinks interrupt flow paths and flow accumulation and prevent water from reaching downstream cells. The fill tool removes these artificial depressions, producing what we call a fill dam, a continuous surface where water can flow naturally without interruption. The input for this tool in ArcGIS Pro is the original DEM, and the output will be filled DEM. Here is a sink-free elevation surface. As I said, this step is absolutely critical. Skipping this step can produce misleading runoff or accumulation patterns. If we skip fill, the water network becomes fragmented, flow direction can't be calculated correctly, and every subsequent hydrological result becomes scientifically invalid. The second step is about the flow direction tool, which is defining water pathways. Once we have a hydrologically corrected surface, we calculate a flow direction. This tool assigns the direction of downhill water movement to every cell, identifying which neighboring cell water will flow into. Flow direction creates the backbone of the hydrological network. The input for this tool is the filled DEM. The output will be a flow direction raster. This raster encodes the movements of water across the terrain. Every following operation, such as accumulation, channel extraction, and watershed delineation, depends directly on this surface. Without accurate flow direction, we don't know where water goes. The step 3 is about a flow accumulation tool, calculating upstream contribution. With the flow pathways defined, we compute a flow accumulation. This tool calculates how many upstream cells contribute flow into each location. Essentially, it answers the question, how much water converges here? Cells with the low accumulation represent hill slopes, while cells with high accumulation represent stream channels and potential collection zones, ideal for rainwater harvesting ponds, or assessing food risk, the prime candidates for rainwater harvesting sites. The input of this tool is the flow direction raster, and the output will be a flow accumulation raster. These results allow us to map a drainage network, locate natural collection points critical for rainwater harvesting, flood analysis, and erosion assessment. The fourth step will be is the watershed. Here is the delineating catchment areas. The final hydrological step is defining the watersheds, the spatial boundaries of drainage basins. Where we can use in the flow direction raster and pour points, specific outlet locations such as the stream junctions or proposed pond sites. The watershed calculates the entire upstream area that contributes a runoff to each point. The input here is a double flow direction raster and the pour points, shapefile or a geodatabase feature. Output will be watershed polygons or rasters representing contributing basins. This step answers the hydrology planner's core question. From where does the water reaching this point originate? Watershed delineation is essential for determining potential water availability for ponds, estimating runoff volumes, linking land cover within each basin to hydrological response. Next, we delineate watersheds using the flow direction raster and defined pour points. This step identifies the area that contributes water to a specific location. These catchment areas are essential for understanding water availability, planning for ponds, or integrating with land cover data for suitability modeling. In the decision input, we are talking now about weighted overlay analysis. This is, we talked the last session, weighted overlay analysis here for hydrological modeling, which becomes truly actionable when integrated with multi-criteria decision analysis. Here we apply weighted overlay, combining multiple layers. Flow accumulation, the high weight, we seek zones of high water concentration. Or when we talk about a slope criteria, the high weight, we can take the moderate slopes, which minimize erosion risk and maximize storage stability. The land cover, the bare soil is the high weight. Construction avoids agriculture and vegetated areas. Each one of these criteria receives a rank and a weight reflecting its importance. The model produces a suitability map highlighting optimal locations for building rainwater harvesting ponds or irrigation infrastructure. The workflow ensures our analysis is scientifically robust, spatially accurate, and operationally actionable. By integrating these inputs, we translate satellite-derived land cover data into a hydrologically meaningful model, bridging remote sensing analysis with actionable environmental decisions. Finally, we integrate the land cover map from our classification with hydrological layers. This combination allows us to highlight areas with bare soil, gentle slopes, and sufficient water accumulation. These layers become the basic for weighted overlay analysis, directly guiding where rainwater harvesting ponds can be built efficiently. When we move now to the automation, why automation matters. Hydrological modeling workflows involve many sequential steps from DEM pre-processing, flow direction generation, flow accumulation computation, watershed delineation, reclassification, and overlay synthesis. Imagine having to manually prepare DEMs and hydrological layers for dozens of watershed or multiple rainfall scenarios. This would take days. That means manual processing of dams, flow direction, accumulation, and watersheds is time-consuming and prone to errors, and difficult to reproduce across multiple scenarios. Automation is therefore essential. From this point forward, automation through Model Builder and ArcPy ensures that this workflow can repeatable, where we can repeat these steps consistently across dozens of watersheds. Scalable, we can scale up to larger areas. tested under multiple rainfall scenarios, and updated rapidly when new satellite data becomes available. It's scientifically robust. This is here the transformation from manual GIS analysis into professional hydrological modeling at operational scale. The tools of automation, a Model Builder and ArcPy. Now that we understand the role of automation in hydrological modeling, it is important to clarify that not all automation tools serve the same purpose. In ArcGIS Pro, we primarily used two complementary automation environments, which are the Model Builder and ArcPython. They represent two stages of analytical workflow maturity rather than competing tools. Think of a Model Builder as the gateway to automation and ArcPy as the final destination for full analytical control and scalability. The first tool is the Model Builder, which is the visual workflow automation. Model Builder provides a visual drag and drop interface where tools are connected in a logical sequence. For many users, especially those new to automation, this is the ideal starting point. With Model Builder, we can design our workflow quickly, test each step visually and interactively, clearly document the analytical logic. It's teach the beginners how special processes are chained together. We can say that Model Builder is particularly valuable because it makes complex workflows easier to understand, allows learners to see the cause and effect between operations, encourages experimentation without programming overhead. For example, building a hydrological modeling using flow direction, flow accumulation, watershed, and weighted overlay can all be assembled visually in Model Builder. This gives trainees conceptual clarity before introducing the coding complexity. However, Model Builder has inherent limitation. Handling large data sets repeatedly becomes tedious. A true batch processing is limited, often requiring a tool duplication. Conditional logic, such as checking whether a file exists or adjusting behavior based, for example, on data set properties, is difficult or impossible to implement visually. This is where ArcPy becomes essential. So the ArcPython, or the advanced Python automation, is the Python scripting interface for ArcGIS. Unlike the Model Builder's visual design, ArcPy operates through code, providing full programming flexibility, conditional logic using if and else statements, iterations using loops for and while, integration with external Python libraries, deployment as standalone scripts, independent of the ArcGIS graphic interface. With ArcPy, ArcPython workflows are no longer limited to processing one dataset at a time. Instead, we can move into true batch processing, executing the same hydrological model over dozens or hundreds of datasets automatically. This level of automation is what transforms GIS from a mapping tool into a scalable analytical platform. The power of batch processing, which is the practical training scenarios. Let's apply this concept to a real training scenario. Imagine we have designed a hydrological suitability model in Model Builder called, for example, Hydrology Suitability Model. This model integrates, as I step up, them pre-processing, flow direction and flow accumulation, watershed delineation, land cover reclassification, weighted overlay for pond site selection. Now consider two workflows, manual or a model builder only approach. We run the model once for basin 1, then manually reload everything or every step for basin 2, again for basin 3, repeating this process for 10 basins. This approach is extremely time consuming, increase the risk of mistakes, produce inconsistent workflows. Where ArcPy batch processing approach with when we use the ArcPy, we create a list of them files representing the different watersheds, write a simple Python loop that feed each them into the file. We work on it, hydrology suitability model, execute the model automatically, saves each output as a separate suitability map. The result will be 10 complete suitability analysis produced with a single comment. What would have taken hours manually is completed in minutes with full consistency and reproducibility. Why this matters? This capability is not a technical luxury. It is operational necessity in real-world GIS projects. Why? Because a natural watershed, because of national watershed assessments, regional flood risk mapping, agricultural irrigation planning, environmental planning across multiple catchments. No professional study processes one area at a time manually. Projects operate at scales where automation through ArcPy becomes indispensable. From a training perspective, the progressions should be clear. Start with a model builder to teach workflow logic, build, test, and visualize analysis steps, document and communicate a methodology, transition to ArcPy, to scale workflows, handle batch processing, apply conditional logic, and deploy reproducible professional grade models. In other words, Model Builder teaches how workflows work, and ArcPy allows workflows to work at scale. Together, they form the backbone of modern GIS automation, bridging learning environments and real-world operational systems. A key practical training step is converting a model builder workflow into a Python script, demonstrating how GIS automation scales from learning tools to professional operational workflows. Building hydrological model with Model Builder in ArcGIS Pro is before moving into Python scripting and ArcPy, we must first master the Model Builder, because this is the environment where we design the scientific logic of automation visually before translating it into code. Model Builder is a powerful component of ArcGIS Pro that allows us to create, edit, and manage geo-processing workflows in an interactive visual environment. It enables us to connect the GIS tools step by step within a structural sequence, transforming complex analytical thinking into an understandable flow diagram. So a model builder plays a crucial role. It teaches the logic of data dependency. I repeat it to fix the information, documents every analytical step and automation repetitive GIS operations without the immediate need for programming. Think of Model Builder again as the blueprint of your analysis. Just as engineers sketch before constructing, we design our hydrological workflows visually before coding them in ArcPy. The core component of Model Builder workflows. Every model builder consists of three essential components: tool, variables, and connectors. Tools, the yellow rectangles represent processing tools. For example, the fill or flow direction, flow accumulation tool, or the watershed. Each tool performs a defined scientific function in our hydrological analysis. When we talk about variables, variables appear as ovals, color-coded based on their type. Green ovals represent data variables such as input DEM datasets, filled DEM surface, raster outputs. The blue ovals represent value variables such as threshold values, reclassification rules, weighted factors. Variables act as the carriers of data and parameters through our workflow. The connectors, which are the arrows, link variables to tools, showing the precise direction of data flow within the model. They express scientific logic. Outputs from one tool becomes inputs to the next. No tool runs in isolation. The full workflow operates as an integrated chain. Building the hydrology model in Model Builder. Hydrological modeling requires a strict order of operations. In Model Builder, we interface this scientifically correct sequence with the complete transparency. Hydrological workflow becomes a single connect chain. Step 1, fill 2, we begin by dragging our digital elevation model into the Model Builder canvas as the initial input variables. We then connect this DEM to the fill tool. The output, a new variable called filled DEM, a corrected surface ready for hydrological pre-processing. I don't enter the details. Step 2, flow direction tool. Next, the filled DEM is connected directly to the flow direction tool. And the output flow direction raster, which is fundamental driver of all subsequent hydrological tools. Next, we add the flow accumulation tool and connect it to the flow direction raster, where this tool calculates how many upstream cells drain into each cell across the terrain. High accumulates value corresponds to stream channels, etc. The output will be flow accumulation raster used to identify natural runoff corridors and water collection points. Finally, we apply the watershed tool. This step requires two inputs here, a flow direction raster and the pour point. The tool delineates every upstream cells that contributes wet water to each PowerPoint, as I mentioned. The output watershed catchment boundaries representing full contributing basins. These polygons define the hydrological units on which water harvesting or management decisions are based. As a summary of hydrological workflow in Model Builder, the required data flow is structured as DEM, fill, flow direction, flow accumulation, watershed. Each step is dependent on the output of the previous step, meaning you can't skip tools. The sequence is scientifically important. Model Builder visually enforces this dependency for clarity and correctness. The advantage of a model builder for hydrological modeling, Model Builder provides several critical advantages for both education and professional GIS workflows. In a visual diagram, instead of remembering the workflow abstractly, the model itself becomes a living diagram of hydrological logic. The entire scientific process is displayed graphically. Each box means a scientific operation, a hydrological calculation. Each arrow means a data dependency. Each oval, an input or output data set, each output validated input for the next computational stage. This ensures no steps are skipped, the sequence remains scientifically valid, the workflow becomes transparent for validation and teaching. Easy modification. Any tool or input can be changed instantly. Swap dim resolutions, modify pour points, or adjust the thresholds parameters without rebuilding the entire workflow. Built-in documentation, the model itself becomes a formal technical documentation that can be reviewed by other analysts, can be shared with collaborators, serves as an audit trail for reproducibility. The batch processing capability. Even inside Model Builder, we can run workflow on multiple DEM files, several watersheds, repeated scenarios. This is the first step toward large-scale automation, which we fully achieve with ArcPy. Before we automate anything further, we run the entire Model Builder workflow once manually. So we want to test the model. Check that all outputs generate correctly. Confirm that a flow accumulation aligns with mapped drainage lines. Verify that watershed boundaries match topographic expectations. Only after this scientific validation, we can say now our model is ready for automation. At this point, you must understand that Model Builder is not a replacement for science. It is a graphical representation of scientific logic. Every yellow toolbox you see in Model Builder becomes one Python command in ArcPy. Model Builder teaches us the logic visually, while ArcPy executes the same logic programmatically at scale. Once we fully understand the flow inside Model Builder, moving to Python scripting no longer feels like a leap. It becomes a natural technical progression. Model Builder builds the brain of the workflow. ArcPy gives it industrial scale muscles. This concludes the Model Builder Foundation and provides the ideal launch point for transition into ArcPy, which is the advanced automation and batch processing. Let me walk you through this process carefully, step by step. So the first step, building and validating the model. Before any expert, the model builder workflow must already be functional and validated. In our case study, this means that the file hydrology suitability model must be correctly connected from input DM to final weighted overlay output, tested using at least one basin or study area, producing expected and scientifically meaningful results. This step is essential. Never convert a model that has not been tested. Exporting a faulty model simply produces faulty code. Validation inside Model Builder ensures that when converting to Python, the script represents a stable and reliable analytical workflow. The second step is exporting the model to Python. Once your model is verified, we proceed to the actual conversion. Inside Model Builder, open your complete the model, go to the Model Builder ribbon, Model tab, Export to Python file. Here, ArcGIS Pro will then automatically generate a complete Python with a file script representing every step of your model. Behind the scene, this is a powerful translation process. Every geoprocessing tool becomes an ArcPy function call. For example, the fill tool transform to ArcPy fill form. Flow direction always become ArcPy flow direction, and every data set or intermediate result becomes a Python variable. The tool sequence is preserved exactly as in the Model Builder flowchart. At this moment, your visual workflow transitions into a text-based executable geoprocessing script. The third step, reviewing the generated Python script. The next step مش محطوط بالكهرباء. The next step is code inspection, and this is where learning accelerates. Open the exported Python file using any development editor, maybe VS Code, PyCharm, or even the built-in ArcGIS Pro Python. When reviewing the script, actively look for several key elements. First, observe how each tool you used visually is now written as an ArcPy command. For example, ArcPy management field, flow accumulation, ArcPy watershed. The second, identify how inputs and outputs are mapped into variables, DEM paths, output, raster names, temporary processing layers, or etc. Third, note how the processing order matches the exact structure of your original model builder sequence. This reinforces a critical concept. Model Builder is not replaced by Python. The model becomes a Python. Seeing this mapping helps you understand that no analytical logic is lost. Python simply offers the deeper control and scalability over the same workflow. Once the code is reviewed, it's time to run the script to prove that the model conversion succeeds. You have two options. The first option, run inside ArcGIS Pro. Open the Python window or the Run Script panel. Execute the exported script directly. This allows testing while staying within the geoprocessing environment. The option number two, run as a standalone script. Use the ArcGIS Pro Python environment externally. Execute the script like any standard Python file. In both cases, the expected outcome is the script execute without errors. All hydrological layers are generated automatically. The suitability outputs are produced exactly as from Model Builder, but now under complete automation. This step confirms that your workflow is now fully reproducible, portable, ready for batch processing and advanced automation. Why this step is transformational? At this stage, we can make an important conceptual leap. We no longer rely on manual geoprocessing or isolated models. We now possess the ability to scale analysis to any number of watersheds, adapt workflows for multiple rainfall scenarios, update models automatically whenever new satellite classification becomes available. This is the turning point from GIS user to GIS automation specialist. Model Builder teaches workflow structure and ArcPy unlock workflow power. For final integration, to summarize this transformation pipeline, design the workflow visually in Model Builder, validate results inside ArcGIS Pro, export the workflow as a Python script, modify and extend the script for batch processing with loops and logic. Deploy the workflow across entire regions and datasets. Through this process, we move from educational experimentation to professional grade environmental modeling, the capacity to support real hydrological planning and water resources decision-making at a scale. So, in general, satellite-derived land cover classification, terrain-derived hydrological modeling, automation via Model Builder and ArcPy, multi-criteria decision analysis through weighted overlay. We establish a complete GIS workflow that bridges research and application. This approach transforms imagery and elevation data into decision support tools, guiding water harvesting site selection, watershed management strategies, soil conservation planning, suitable land use development. Ultimately, this demonstrates the true value of a GIS, not mapping for visualization only, but modeling landscape for informed action. حنين بدك أنت تحكي شيء أو الدكتور؟ This is the last slide for our today's session, and I hope okay. I will send you the complete assignment in this week, and you must send it for the email that you mailed. And this is very interesting to have the certificate from LCWE and Esri Lebanon. Thank you all for your participation, and meet you, inshallah, in other courses for GIS. Thank you. One meeting. Allah يفضل.